Greeting of the day. Myself, Dr. Naga Jyothi, working as assistant professor in ECE department. Today we are going to learn about in digital electronics. We have many concepts in that we are going having circuits are in digital electronics. Circuits are divided into combinational circuits, and next one is sequential circuits. So in combinational circuits, when we are going to change in the input, there will be a change in the output. So present output is depends upon present input in the combinational circuit. Whereas in sequential circuits, input not only depends upon present input, output not only depends upon present input, it also depends upon the previous output, and also there will be a controlling will be present in the sequential circuits. So today for the combinational circuits we have an example of adders, multiplexers, demux, decoder, encoder. All this will come towards the combinational circuits. Whereas in sequential circuits we have flip-flops, shift registers, counters. All this will be come towards the sequential circuit. Today we are going to learn especially on the flip-flops. So why? Because all the sequential circuits are depends upon the memory elements. So memory elements plays a essential role in all the components. In memory elements we have again latch and flip-flop. So what is the main difference between latch and flip-flop? Before going to that, what is meant by latch and what is meant by flip-flop? Latch is a level triggered signal. Latch is a level trigger. Whereas flip-flop is an edge trigger. Whereas flip-flop is an edge trigger. So in edge trigger again we have positive edge circuit and negative edge trigger. Negative edge trigger circuit. So when we first one is what? Latch. So in latch what happens means if we give an input 0, then there will be an output 0. If you give an input 1, then we are going to get output 1. So this one we are going to be call it as a transparent latch. This type of latch we are going to be call it as a transparent latch. And next second one is gated latch. In gated latch what happens means there is an enable controlling signal, call it as an enable pin, and input will be present and output. So what is meant by enable and how it will be going to be varied. So let us consider a signal, input signal like this. This one as input, and let's take another signal, this one as enable. Then how the output will be? When enable is on or high, when enable is high, whatever the input is there, it will be reflected towards the output. So when enable is high, so whatever the input is there, it will be reflected. When enable is low, whatever the input is there, it won't reflect. See, after here, all the enable is high. Here the value is 0. When enable is low, output is also low. When you observe in this case, what happens? See here Here the level is 1. So whatever the output is there, it will be reflected again. Here, up to here. But when up to the high value, the output is high. Afterwards, again it will be 0. So this is about, so here in output is varying according to the levels. According to the levels, output is going to be varied. That's why you are going to be call it as a level trigger circuits. Latches are level trigger. Next we go for flip-flops. So already we have mentioned that flip-flops are edge trigger. We have two types of edges, edge triggers. One is positive edge trigger and second one is negative edge trigger. So what is meant by positive edge triggering? In the clock, if input is 0 to 1, in the clock, the signal 0 to 1 rises. At that time, output is going to be varied. Then that one you are going to be call it as a positive clock, positive trigger. And if we have negative vary, 0 to 1 means negative value. So this one you are going to be call it as a negative edge trigger. Based on this, the flip-flops are going to be divided into 4 types. They are SR flip-flop, JK flip-flop, D flip-flop and T flip-flop. Today we are going to design SR flip-flop using NAND gate. SR flip-flop using NAND gate. So when you observe here, we are going to designing flip-flop using NAND gate. In this, output of this flip-flop NAND gate is going to be given as input for this NAND gate, and output of this NAND is going to giving for this NAND gate. Let's take A0, A1, A2, A3 NAND gates, and let S and R. For these two, I am going to giving clock as a controlling signal. See now, so for this, let us take the outputs as Qn plus 1 and Qn plus 1 bar. So when clock is high, irrespective, when clock is high, with the combination of SR, the outputs are going to be varied. When clock is low, irrespective of the inputs, output is undetermined. So clock SR Qn plus 1, Qn plus 1 bar. When clock is low, irrespective of inputs, outputs are undefined or whatever the previous values you have. When clock is high, we have the combinations of 4 combinations are there. So those 4 combinations are 0, 0. When clock is high, 0, 1. When clock is high, 1, 0. Clock is high, 1, 1. So when the inputs are 0, 0 and clock is high means 1. So we know that truth table for the NAND gate, when any one of the input is low, output is high. According to this concept, what happens means, here it is 0 and here is also 0. What is the, here we are going to getting output of 1, 1. Now we are going to, so as here 1, 1, NAND output of this gate is depends upon the second input. To determine that, we have to assume first, here we have taken Qn plus 1. So let us consider previous value is Qn and let's take that value as 0. If it is 0, Qn bar means what happens? It will be 1. So if here it is 0 means this 0 will comes here and this 1 will be coming here. 1 1 1 1 for the NAND gate output is 0 and 0 1 for the NAND gate output will be 1. So if we assume previous value as 1 and this one take it, if it is 1 means automatically we will get as 0. Then here the value will be 1 and here the value will be 0. If 1 0, what happens? Again the output will be 1. 1 1 means output will be 0. So for SR flip-flop, when clock is high and the inputs are 0 0, the outputs will depends upon the previous values. The output will be depends upon previous value Qn and Qn bar. Next combination is 0 1. So 0 1, R is equal to 1. Then what happens? Let us take. When R is equal to 1, so as we know, if any one of input is 0, output is 1. And again here 1 1 means output is 0. Irrespective, here 0. See here, irrespective of the other input, output will be 1. Why? Because as any one of input is 0, output for NAND gate is 1. This one is going to given again here. So 1 1 means what is the value? 0. So for 0 1 inputs, output will be 0 1. And next combination is 1 0. 1 0. So now S is equal to 1, R is equal to 0. So as R is 0, irrespective of another input, what is the output? 1. And again 1, 1. 1, 1 output is 0. So as this one is 0, output for this NAND gate is 1. This one again we are going to giving here. 1, 1 means 0. This 0 again here coming. So for 0, 0 combination, 1, 0. 1, 1, here the output will be 0. So for 1, 0 combination, the output will be 1, 0. Next last combination is 1, 1. 1, 1. So when you observe here, S is 1, R is 1, clock is 1. 1, 1 means here it will be 0. 1, 1 means here it will be 0. Irrespective of other inputs, output will be 1. And here Qn plus 1 output is 1 and Qn bar n plus 1 bar the output is 1. So according to rules, if here the output is 0 means here the output of Qn bar will be 1. If Q is 0, Qn bar is 1 and if Qn is 1, Qn bar will be 0. So this one we are going to be called as an undetermined by, because in both cases the output is 1 1. To overcome this, we are going for JK flip-flop, and in that this problem is also known as race around condition, and we are going for this. To overcome, we are going for next flip-flop is JK flip-flop. In this JK flip-flop, what happens means same like the SR flip-flop, but little bit change. Here this one is Qn plus 1 and this one is Qn plus 1 bar, and here we are going to take in clock, and this is S and this is R. For this again we are taking this Qn towards here. And the Qn bar is going to be connected to the NAND gate. Now this will be Qn plus 1 and this will be Qn plus 1 bar. When you observe here, now the again combinations S, R, clock, Qn plus 1 and Qn plus 1 bar. When clock is high and 0 0. So repeat it. Sorry. Now we are going for JK now. So take it JK. This flip flop is known as JK flip flop. When 0 0 we have taken. So consider now 0 0 and clock is high means 1 1. So irrespective of this will be 1 as input is 0, this is 1, and when you observe this is also 0 1 as one of the input is 0, output is 1 irrespective of other inputs. So when you observe here 1 1, again it depends upon the previous value. If we are going to take in previous value 0, what happens here? It will be 0 and here it will be 1. 1 1 means 0, 0 1 means 1. So same like the SR flip flop, you will get Qn and Qn bar. For clock is high and it is 0 1. So we are 0 1 we are going to get 0 1, 1 0 you are going to be getting 1 0. For 1 1 which is the problem in SR flip flop, we are going to be overcome here by considering 1 1. J is equal to 1, K is equal to 1. So when J is equal to 1 and K is equal to 1, so clock is 1. Now here we having Qn plus 1 bar. Here we are having Qn plus 1. Now previous value let us take Qn as 0. Then we are going to here 1. As here 0 1 1. What happens? As one of the input is 1. One of the input is 0, output is 1. Here all are 1s, so output is 0. As this is 0, irrespective of other input, it will be 1. As this is 1, here also we are going to getting 1. 1 1 means output is 0. So when Qn is 0, Qn plus 1 will be 0. If Qn is 1, now Qn is 1. 0. Qn is 1 and this will be 0. Then what happens? See. So all three are 1s, output is 0. 0, 1, 1. This is 1. As this one is 0, irrespective of this one will be 1. As this one 1 is here, we are going to giving 1 1 means you are going to getting 0. So it will be reverse of the value for 1 1 Qn bar and Qn. So whatever the race around condition problem is present in SR flip flop, it was overcome by using JK flip flop.